Hello there, this is Ms. Page, and in this lesson we are going to talk about how to solve right triangles, which means that we have to find all of the unknown measurements, sides and acute angles. So previously you have learned about the basics of trigonometry called sine, cosine, and tangent. Sine, cosine, and tangent are ratios of two sides of a right triangle. And we will be using this in some of our problem solving for our right triangles in this lesson. So here what we're looking at is making sure that we know our ratios. So if we're looking at this from the perspective of angle A, one of the acute angles in our right triangle here, then the sine of angle A is the side that's opposite angle A divided by the hypotenuse, where again, remember, your hypotenuse is always the side that is across from your right angle, also always the longest side in a right triangle. Cosine is the side adjacent or next to angle A, which would be this side here, over the hypotenuse, and the tangent of our angle A is the side opposite angle A, which means across the triangle from angle A, divided by the side adjacent. So it's super important that in these problems we can identify which sides are which relative to whichever angle measurement we are working with. If we know if we're solving for an angle measurement using trigonometry, a sine, cosine, or tangent ratio, and the unknown is the angle. So if we don't know what angle A is, but we do have numbers for the side opposite and the hypotenuse, we're basically going to set up this equation and then solve it. You might also remember doing these problems previously. So to undo sine, we use its inverse function, which we call sine inverse, and it's written here like this. So we would take the sine inverse of both sides of our equation here, and that's what this is giving us over here. So over here, sine and sine inverse would undo each other, leaving us with angle A. That corresponds to what this says here, and then calculating that measurement, we use our calculators to calculate the sine inverse of this ratio, side opposite over the hypotenuse. Similarly for if we're working with a cosine ratio or a tangent ratio. This is an outline basically of kind of based on the given information, the best practice as far as how you work through a problem to make sure that you get the most accurate values for both sides and angles. In order to solve a right triangle, like I said, it means that you're finding, so solving a right triangle means you're finding the lengths of all unknown sides and the measures of all unknown acute angles. We always know the largest angle measurement, that's our right angle, so we'll never have to solve for that one. But we may have to solve for one or both of the acute angle measurements. In order to solve a right triangle, to actually be able to figure out all the unknown measures, you either need to know two side lengths or you need to know one side length and one of the acute angle measures. Whenever possible in your problem solving, you should use exact measures to solve the triangle. That will make sure that you get the most accurate answers for each measurement, which is always expected. All right, let's take a look at a problem. So in this problem, we are going to solve the triangle, which, as I said, means that we're going to find all unknown measures and angles and sides. And we need to keep track of what those are and know the proper way to write those notations too, given this type of problem. What we're looking at is here, we have some instructions to round any side lengths to the nearest tenth. And that would be our centimeters. And we're to round angles to the nearest degree, which would be the nearest whole number degree measurement. So in this diagram for our triangle ABC, a couple of things you need to be aware of is how we name sides in a triangle is with the lowercase letter of the angle that is its opposite. So if this is my angle A, then across from it, this 2.7 centimeter measurement, that would be called side A, using a lowercase. across from our right angle here of angle C, which is our hypotenuse of 3.1 centimeters, that would be lowercase c or side C. And across from our angle B would be side B with a lowercase b. So the measurements we need to realize here that we have to find are going to be side B, of course, because we can see that, but also our two acute angle measurements, angle A and angle B. So that's what we need to find. And one of the things that I notice is that people don't always recognize or remember about angles. So it's a good idea to write these things down. So we have angle A and angle B. These are the three things or measurements that we need to find. All right, so best practice. We know two sides of our right triangle. We should then, finding this third side, use these two sides, which means that we would use the Pythagorean theorem to find side B. And I'm going to do that first. So side B, I would use my Pythagorean theorem, a squared plus b squared equals c squared. So my A is 2.7. And my C, my hypotenuse, is 3.1. So B is going to be the square root of 3.1 squared minus 2.7 squared. And this is a side, so we're going to round it to the nearest tenth of a centimeter. All right, so now we can use our calculators. All right, and hopefully you come up with the same measurement I'm getting, which is about 1.5 centimeters to our nearest tenth. So there's one measurement found. So now what remains is our two angle measurements. And here we're going to have to use a ratio of sine or cosine, whichever one we start with first. It doesn't really matter whether we find A or B first. All right. So I'm going to go ahead and find A. So my second step is I'm going to find the measure of angle A. So what I have in order to find A is, again, I want to use my exact measurements that I was given, which are the 2.7 and the 3.1. The 2.7, which is side A, is across from or opposite to angle A. So this is my side opposite. The 3.1 is my hypotenuse across from my right angle. So I have to know that opposite over hypotenuse is my sine ratio in a right triangle. So that tells me that the sine of our angle A will be equal to the ratio of the opposite side of 2.7 to the hypotenuse of 3.1. Here's where we have to undo the sine function. So we undo functions with their inverses, and the inverse of sine is called sine inverse and is written with a superscript of -1, our inverse notation. So we take the sine inverse of the sine of angle A, and we also, of course, for balance in our algebra, have to take the sine inverse of the other side, which is our ratio. So over here, our sine and sine inverse will undo or cancel each other out, leaving us with our angle A. And now we can take this and use our calculator on this to approximate our angle measurement to the nearest degree. So we're going to get angle A is approximately a certain number, whole number of degrees. To put this into your calculator, you'll notice in your calculator, the classroom calculators, that this is the second function above the sine key. So you hit second and then sine, and it should pull up this symbolism, the sine inverse notation. If it does not open a parenthesis, make sure that you do, because your ratio would need to be in your parentheses in order for the calculator to know that that entire ratio is your sine ratio that you're taking the inverse of. All right, give it a try. So to the nearest degree here for angle A, we get 61 degrees. Make sure you've got that degree symbol. No degree symbol, then you're actually measuring in a different type of angle unit, which we call radians, and they're not equal to one another. So 61 degrees and 61 radians are not the same angle measurement, so that degree sign is required and super important. So now we have one more measurement to find, and that is the measure of our angle B. You might be thinking that we'll do the same type of thing, but we will not. And the reason is because of the triangle sum theorem. The triangle sum theorem, if you recall, says that the three angles of any triangle will add up to 180 degrees. If we use trigonometry, like a sine, cosine, or tangent ratio to find the second angle, with the rounding that we're doing, there's the possibility that our three angles will not add up to 180 degrees. So best practice will be to find the second angle to use the triangle sum theorem. And the triangle sum theorem says that angle A plus angle B plus angle C must add up to 180 degrees. So we will use the 61 degrees for our angle A. We're finding B, and we'll use our 90 degrees for our angle C. And that will then allow us to get the best answer here for angle B. It is technically still approximate, quite honestly, at this point, because 61 is approximated. So that will make our B an approximate angle measure also. So subtracting the 90 and the 61 both from the 180, you should be getting a value of about 29 degrees to the nearest degree. So that finishes all of the measurements that we didn't know, which means the triangle is now solved. All right, so moving on, here we have a practice problem. I would encourage you to pause the video here, give yourself some time to work this out before the solutions are revealed. All right, so here are the solutions. So side P, which is the side across from angle P here, you should have about 16.1 inches. And then angle P is about 64 degrees, and angle Q is about 26 degrees. All right, here's a second practice problem. Solutions here. So side D, which is across from angle D, which is the right angle in this case, so that's our hypotenuse, is about 17.3 centimeters to the nearest 10. Angle E is about 32 degrees. Angle F is about 58 degrees. One of the things I did want to mention, so if you found angle E first, you would have used a tangent ratio of 9.2 over 14.7. If you found angle F first, you still would have used a tangent ratio, but it would have been 14.7 over 9.2. In the previous practice problem, if you found angle P first, finding angle Q first, you're using a sine ratio because 8 is opposite angle Q and 18 is your hypotenuse. However, if you found angle P first, you would have used a cosine ratio because 8 would have been the adjacent side to angle P, and you would have had adjacent over hypotenuse. All right. Now we're going to do this second example together. Notice in this one we are not given a picture of a triangle, which means that we have to interpret what we're reading here about the triangle, make sure that we draw the triangle and label it correctly, so that then when we do our math, the math is the correct math that corresponds to the correct triangle for the values we're supposed to get. So we know we have a right triangle. We're supposed to solve that triangle. And here it gives us some information. If you are not familiar with this notation, this is saying that side PQ of our triangle is perpendicular to side PR. That means that those two sides form the right angle. And the point or vertex of the triangle where that right angle is located would have to be the point or vertex that they have in common, the two sides have in common where they meet, which here is the letter P or point P or angle P. You could look at it all those ways, which means that I'm looking at my triangle having, not that little thing, but my right angle here would have to be an angle P, and say that this is then Q, and this is R. So this gives me side PQ, this gives me side PR that are now perpendicular to each other, and connecting Q and R then forms the hypotenuse of the right triangle. So here it says QR is 47 millimeters. QR corresponds also to side P with a lowercase. That is our hypotenuse. The measure of angle Q is given as 52 degrees. So I have drawn Q up here in this corner, so that's my 52 degrees. Again, I am expected to round my side measurements that I find to the nearest tenth, and I'm expected to round any angle measurements that I find to the nearest degree. So the things that I'm going to have to find, so here I have angle R, so this would be side R. And here I have angle Q, so across from it, this would be side Q. So what I have to find will be side R, side Q, and the measure of angle R. Those are the three things I don't know. All right, so with the given information that I have, what I would actually find first is angle R. And angle R is actually not going to be an approximation because I'm going to use my triangle sum to find angle R. So the measure of angle R, I'd use the triangle sum theorem, which says that angle P plus angle Q plus angle R must add up to 180 degrees. Angle P is my right angle. That's an exact measurement. Q is given as an exact measurement of 52 degrees. And so that's going to make angle R an exact measurement once I do this math of subtracting the 90 and the 52. So my angle R is going to be exactly a certain number of degrees. And that number of degrees will be 38. So first part is now done. So now what we are going to do is move on to either finding R or Q. Honestly, it really does not matter which one. There's no better choice of which one we now decide to find. So I wrote R first. I'm just going to find R first. So second step is I'm going to find side R. Now, for finding side R, I want to use exact measurements. Technically, I could use either the 52 or the 38 that I found here for angle R, and then I need to use my 47 millimeters. I'm going to go ahead and use what was given. So with my finding side R here, what I'm going to do is use angle Q. Relative to angle Q, side R is my adjacent side. And the 47 millimeters, as I previously said, is the hypotenuse because it's across from the right angle. So now I need to know that adjacent over hypotenuse is my cosine ratio. So my equation becomes the cosine of 52 degrees is equal to the side adjacent, which is side R, over the hypotenuse of 47 degrees. So the math in this case, I would multiply both sides by 47. And that is going to give me then an R value of 47 times the cosine of 52 degrees. So now to get a measurement to the nearest tenth, I'm going to use my calculator. This calculation is pretty straightforward. 47 times cosine 52 degrees. 52 degrees should be in parentheses. If you are having issues, you do have to make sure that your calculator is in degree mode. Like I said, there are other types of angle measurements that we can use our calculators to calculate with. So we need to make sure that the calculator interprets our angles as a degree measure to get the right answers. So check your mode to see if you're not going to able to get the correct answer, which is 28.9 millimeters to the nearest tenth. All right, so next we have our third measurement, which is side Q. Some of you might be thinking that we're going to use our Pythagorean theorem here now. We are not. And the reason is because to use our Pythagorean theorem, we have to use side R, which is not an exact value. It is an approximate value. So we are going to use another trig equation similar to what we have here for our cosine. But this time, if I want to find side Q, side Q is across from or opposite to my angle Q that I've been using. So that means I have a ratio of opposite over hypotenuse, which is my sine ratio. So best practice to make sure we get the most accurate answer would be to say the sine of that 52 degrees would be the ratio of side Q over the hypotenuse of 47 millimeters. And then multiplying both sides by 47 tells us side Q will be 47 times the sine of 52 degrees. And now we can use our calculators, and rounding to the nearest tenth, we should get about 37.0 millimeters. You'd need that 0.0, remember, because that's in the tenth spot, which is what we are rounding to. All right, so that finishes this problem. We have found the 3 unknown measurements. There will always be 3 when we are solving a right triangle of this type. And so now we can take a look at a practice problem. So again, I would recommend you pause the video here, give yourself a chance to try this one on your own, and make sure that you are understanding everything. All right, so for the solutions here, you hopefully got that angle A is exactly equal to 56 degrees, that side A, which is across from angle A, so here's your triangle, so B, which is your shared end point, that is where your right angle would be located. And then you have AB, which is this side, and BC, and then that becomes your hypotenuse. So A, which is across, that's opposite, actually with your 34 degrees, if you use that, that would have been a cosine ratio if you used that. And then you are dealing with, tangent ratio. Tangent ratio for angle A, or side A rather, because the 29 centimeters that we were given is side AB, which is going to be opposite our angle C of 34 degrees, and this would be our side adjacent to that. And opposite over adjacent is our tangent ratio. If you had some trouble with the math here, remember you just undo your division, multiply both sides by A, and then you'd have A times your tangent of 34 degrees, so then dividing both sides by the tangent of 34 degrees gives you the 29 divided by the tangent, 34 degrees, which is shown here. And that then is what you'd use your calculators to calculate, giving you the 43.0 centimeters. And then using our exact measurements, we use a sine for our side B, where B is our hypotenuse. So similar, we have a B in the denominator here, so we multiply both sides by B, and then divide both sides by the sine of 34 degrees, which gives us B is this ratio, which is about 51.9 centimeters. All right. Here's another practice problem you can give a try. And so here are your solutions to this one. Angle N is exactly 23 degrees. It's a tangent ratio using your 67 degree angle, which was given, of h over 15.6, and it's a cosine ratio using the 67 degree angle of 15.6 over k to find side k. So again, you'd have to multiply both sides by k and then divide both sides by the cosine of 67 degrees to solve for k, which is about 39.9 feet in this case. All right, one final thing. Oh, another practice problem. Okay, give this one a try if you would like. Here are the solutions. Angle Z is exactly 72 degrees. Side X about 11.7 centimeters. Side Z about 36.1 centimeters. So using our 18 degree angle, which is angle X, to find Z, we're using a cosine ratio, and to find X, we are using a sine ratio. And another one. We have a lot of practice in this one. So for this one, we're looking at finding side T first, using our Pythagorean theorem, which is the hypotenuse. So here's our math here. That's about 5.6 inches. And then here the tangent ratio has been used for angle B, where 5.4 is the side opposite to angle B, and 1.3 is the side adjacent to angle B. So that gives us then, taking the tangent inverse of both sides, this we can use our calculator on and rounding to the nearest degree, it's about 76 degrees. And then remember, For the next one, we use our triangle sum theorem, and so that gives us an R of 14 degrees. If you found R first and then B, you should get, relatively speaking, still the same values. All right, here is now finally our closure. So one of the things that you do need to be aware of is when you're solving a right triangle, in what parts of the problem should an inverse trigonometric function be used? So take a moment and think about what parts of the problem, what you're solving for that requires the use of an inverse trigonometric function. All right, so hopefully you came up with an explanation or an answer that's similar to this one. So when you are solving a right triangle, you're going to need to use an inverse trigonometric function when you know two side measures and you are solving for one of those acute angle measures. So that's when you have like sine of angle A equals a ratio of two numbers, and you need to undo sine, or you have cosine of angle B or tangent of angle D, and you need to undo the sine, cosine, or tangent. That's when you're going to have to use that inverse trigonometric function on both sides, remember. All right, that ends this lesson, and you should be ready now to begin your assignment. Have a good day.